understand that there is a line impedance at each of the line connecting the load 1, load 2 and load 3. And by analyzing the circuit, we can understand that the voltage at load 2 is the additions of voltage at line 3 until 4 and the voltage at load 3, whereas the voltage at load 1 is the additions of voltage at line 2 until 3 and the voltage at load 2. And lastly, the voltage supply is the voltage addition of the voltage at line 1 until 2 and the voltage at load 1. Now, by understanding the given parameter, we will know that to find the impedance at each of the load, we will have to start from load 3, as the voltage is given for load 3 only, which is 240 with the angle of 12 degree VRMS. To find the Z load for load 3, it is simply by using the formula S, which is the apparent power, is equals to the voltage squared divided by Z load conjugate. So by changing the place of each of the parameters, we will have the Z load 3 is equals to V squared divided by S apparent power conjugate. This formula is also used when finding the impedance of the load at load 2 and also at load 1. So, when using this formula, we will have to know firstly the voltage of each of the load, except for load 3, because the voltage at load 3 is given as 240 with an angle of 12 voltage. The calculation is as shown with a Z total of 0.6588 with an angle of 11.81 degree ohm. Next, for the main supply voltage, as discussed before, voltage supply is equals to voltage at load 1 added with the voltage at line 1 until 2. And the voltage supply is 248.457 with the angle of 14.42 degree volt. For the current flow in the system, we are using the formula of S, which is the apparent power, is equals to voltage multiplied by the current conjugate. And by changing the positions of the parameters, we can find the current for each of the load by dividing the S apparent power with the voltage at each of the load. The total current for the system is equals to 377.166 with an angle of 2.61 degree ampere. Next, we want to know the real and the reactive power losses at the transmission line. So we will use the formula S is equals to voltage multiplied by current conjugate. So when calculating the apparent power, we will have the answer in rectangular form. And in rectangular form, the real number is the real power, whereas the imaginary number is the reactive power. The answer for our calculation is as shown. Next, we want to know the total apparent power, the real power and the reactive power of the systems, and we want to determine whether the system is leading or lagging. This is easy by adding the total apparent power, which is the apparent power at the line 1 until 2, line 2 until 3, line 3 until 4, and the apparent power at each of the load. And the total apparent power is 93.709 kilo with the angle of 11.81 degree voltage ampere. The total power losses is 91.727 kilowatt, whereas the reactive power is 19.178 kilo reactive power. And by checking the angle of the apparent power, we can know that the system is lagging because the angle is not in negative, it is in positive.
Measuring current at load 1, load 2, load 3 and total supply current. So to measure these values, we use single frequency AC analysis, and as shown here, the frequency is 60 Hz and the complex number format is magnitude and phase. So at the output, these are the variables: IR1 is current at resistor 1, which is equal to the total supply current, and IR load 1 is the current at load 1, IR load 2 is the current at load 2, IR load 3 is the current at load 3. So we run the simulation, and these are the values. This is the magnitude, and this is the phase in degrees. So this is the total supply current. This is current for load 1, current for load 2, and current for load 3. Measuring real and reactive power at transmission lines. First of all, to measure real and reactive power at transmission line 1 to 2, we use probes. So for voltage, we use a differential voltage probe, and we place it here, and the reference we place it here. And for current, we use current probe and place it here in the middle, and we use single frequency AC analysis, and frequency is 60 Hz, and the complex number format is real and imaginary. At the output, we use this expression, which is V PR1 times conjugate I PR2. V PR1 is the voltage measured by voltage PR1 by the probe PR1, and I PR2 is the current measured by this current probe here. So we run the simulation, and we get these values. So this is the real power, which is 853.50927 watts, and this is the reactive power, which is 1.70702 kiloVars. To measure real and reactive power at transmission line 2 to 3 and 3 to 4, the process is the same as for transmission line 1 to 2. So we place differential voltage probe as shown here, which is PR3 and PR5, and we place the current probe in the middle as shown here and here. So in the single frequency AC analysis, and at the output, these two are the expressions. This one is the expression for transmission line 2 to 3, which is VPR3 times conjugate I PR4, and this one is the expression for transmission line 3 to 4, which is VPR5 times conjugate I PR6. So we run the simulation, and these are the values. So this one here, which is 676.43 watt and 1.35286 kilovars, is the real and reactive power for line 2 to 3. And this one here, 194.99699 watts and 487.492 vars, is the real and reactive power for line 3 to 4. Measuring total real and reactive power, total apparent power, and power factor of the system before power factor correction. To measure the total real and reactive power, we use single frequency AC analysis. So complex number format, we set it to real and imaginary, and the frequency 60 Hz, and at the output we use this expression, which is V5 times conjugate IR1. V5 is the voltage at the line here, which is equal to voltage of V supply, and IR1 is equal to the total supply current. So we run the simulation, and we get the real power and the reactive power of the system. And from the values that we obtain, we can observe that the imaginary value, which is the reactive power of the system, is positive. Therefore, the system is a lagging system. To measure the apparent power, we simply change the complex number format from real, imaginary to magnitude and phase. And at the output, we use the same expression and we run the simulation and we get these values. And the magnitude obtained, which is 93.70866 kilowatt, is kVA, is the total apparent power of the system. For power factor, to measure the power factor of the system, we use wattmeter, and it is connected like this, and we run the simulation and check the wattmeter, and the power factor is displayed here, which is 0.98. Therefore, the power factor of this system is 0.98, lagging. Measuring total, real, reactive, and apparent power of the system, and also power factor of the system after power factor correction. So for power factor correction, we want to change the power factor of the system from 0.98 lagging to 0.98 leading. So this is done by connecting a shunt capacitor of value 1.624 millifarad to the system. So as you can see here, the shunt capacitor is connected to the circuit. So let's see the new real, reactive, and apparent power and also power factor of the system. So we use single frequency AC analysis, and we use real and imaginary values. At the output, we use this expression and we run the simulation, and we get the real power and the reactive power here. And as you can see here, the reactive power is a negative value. Therefore, the system has changed from a lagging system to a leading system. To measure the total apparent power, we change it to magnitude and phase, and we run it, and change it to magnitude and phase, and run the simulation, and this is the magnitude that we obtain, which is the total apparent power of the system after power factor correction. And the power factor of the system, we used wattmeter, and as you can see, the power factor is still 0.98. Therefore, after adding this shunt capacitor of value 1.624 millifarad to the circuit, we have changed the system to from a lagging system to a leading system with the same power factor value.